Welcome back. Before I start this video, I have to clarify something. I said in the last video that physicists are sometimes not careful enough in applying theorems, so they can interchange derivatives and sums without paying attention to the right conditions. And actually, I will give a counterexample in the lectures, showing that if you don't put some assumptions, the result may be wrong, the conclusion may be wrong. I didn't mean actually to criticize physicists, because I must say that usually physicists are ahead of mathematicians in their intuition, because they understand better their problems. And for them, usually mathematics is a tool, it's not the goal. So the important problem for them is not really the math, it's the physics. So this is why you may find some differences in thinking. But a mathematician should be more precise and careful and rigorous. Okay, and this quality is actually important. This is what distinguishes pure mathematicians from other scientists, actually. So. Okay, so now let us continue with chapter 3 and move to the next application of the mean value theorem, which studies the notion of strictly differentiable maps, the notion of strict differentiability. Okay, so let us start as usual by the simplest setting of a function from R to R, or from an open set of R into R. You all know that differentiability at a point means the existence of the limit of Newton's ratio. This is what you call Newton's ratio, okay? Or if you like, delta F over delta X. Okay, but now so this is now a function of one variable, X. But what if we consider a function of two variables? If we consider the ratio f of x minus f of y over x minus y, and let both x and y tend to A independently. Okay, so if the limit in one exists, does it follow that the limit in two exists? Actually, you can pause the video and try to think of this. The answer is no, actually, because I'll give you an example. If the limit in 2 exists, then the limit in 1 exists, because just put y equal a. You have the right to do that. Okay. So the limit in 1 is a particular case of the limit in 2. However, the converse is not true, and now I'll give you an example. Consider the function defined by x squared times sine 1 over x if x is not 0 and 0 at 0. Okay. Now, this function is not only continuous, but it's differentiable, actually. It's differentiable at any point different from 0 because it's the product of two differentiable maps. But the only problem is at 0. But at 0, actually, if I write Newton's ratio, f of x minus f of 0 over x minus 0, I simplify by x, of course, if x is different from 0. And I get x sine 1 over x. And since sine is bounded, it's between minus 1 and 1. So as x tends to 0, the product tends to 0. So this means that f is differentiable at 0 and its derivative at 0 is 0. Okay, so the limit in 1 exists for a equal 0. However, the limit in 2 does not exist. Because if it existed, then we should have for any two sequences xn and yn converging to 0, this ratio, this sequence f of xn minus f of yn over xn minus yn should exist as n tends to infinity. But now I will choose in a specific way xn and yn, two sequences xn and yn converging to 0, but such that this ratio does not possess a limit. So I take xn equal 1 over pi over 2 plus n pi, and yn to be just xn plus 1. And these two tends to 0. Okay? However, if you do the computation, if you compute this ratio, you will get, after some simplification, this result, minus 1 to the n over pi times n plus 3 half over 1 plus 1 half plus the inverse. And of course, the term between brackets tends to 1 plus 1, it's 2. But because -1, but we have an oscillating term here, -1, so there's no limit. So if you like, this ratio oscillates between 2 over pi and -2 over pi all the time. So it does not converge. Okay. So this proves that, and if you want to check that, I suggest that you simplify a little bit and set Sn equal pi over 2 plus n over plus n pi. Okay, so there is a little bit of algebra here. It's not difficult, and if you get a different result, don't panic. If there is an error, we'll correct it. But you should get something like this. And I chose, there's the parenthesis here, I chose these two sequences on purpose because I want to compute easily sine 1 over xn. Okay, sine of 1 over xn is sine of pi over 2 plus n pi. So when n is odd, it's -1. When n is even, it's 1. Okay, because sine is 2 pi periodic. Okay, so this gives a counterexample. So 1 does not imply 2. Okay, so we have now another condition, a stronger condition of differentiability that we will call strict differentiability, and some people call it actually strong differentiability or strong Fréchet differentiability. Okay. So this is the definition. So a function defined on an open set subset I of R is said to be strictly or strongly differentiable at the point A if the limit exists. Okay. So this implies in particular that it's differentiable at A. Now, the purpose is to extend this definition to the case of maps between norm spaces. So we do the usual way. We start by rewriting this limit. If this limit is L, then the existence of this limit means that there exists a number L such that f of x minus f of y minus L times x minus y is a small o of x minus y. And of course, you can play with this form. You can write it in so many ways. Okay? Or if you like, in epsilon and delta. So we have this condition. If x and y are sufficiently close to A, then the left-hand side is less than epsilon times x minus y. And now in this form is easily generalizable. So instead of a number, you guess what you should take. We should take a linear bounded operator. Okay. So this is the definition. So we have, as usual, a map defined on an open subset U of a norm space E, and that takes values in another norm space F. So we say that F is strictly differentiable in the sense of Fréchet, or strictly Fréchet differentiable, or if you like, strongly Fréchet differentiable at the point A, if we can find a linear bounded map from E to F such that f of x minus f of y minus this linear term is a small o of the difference for all xy near A. Or if you like, in terms of epsilon and delta, just take norms instead of absolute values because we are working in norm spaces. And of course, instead of the sum, you can take the maximum of these two, or the Euclidean norm if you like, doesn't really matter. Or if you'd like, in terms of balls, so for every epsilon positive, there exists a positive number delta, such that for all xy in the ball of center A and radius delta, we have this inequality. Now, it doesn't really matter if you take an open ball or a closed ball here, as you may check. So I can write strictly less than delta. And I can write here strictly less than epsilon. Doesn't really matter, okay, as you may check. Okay, and now it should be clear that this definition is stronger than the usual Fréchet differentiability that we learned. And the operator L in the definition is exactly the Fréchet derivative of the function f, okay? Because you just put y equal a. Okay. So, but now we have to. So we have a stronger condition, but we want to understand it better. Okay. It seems a little bit mysterious, but it's due to essentially to the mean value theorem. It's not that mysterious. So we'll prove the following result. If f is Fréchet differentiable on an open set U, so throughout the whole domain, and we consider a point A in the domain, then f is strictly Frechet differentiable at A if and only if the derivative of f, which exists because f is Frechet differentiable on the whole domain, if and only if f prime is continuous at that point. So this is really important, but it was not clear from the definition. So strict differentiability means essentially continuity of the derivative. Okay, so there's nothing really mysterious, but it's not clear why this is true, so we have to prove it. Okay, but before we prove it, we need a very useful lemma, which is a kind of converse to the mean value theorem. The mean value theorem in version 3.3 states that if on a convex set the derivative is bounded by some constant m, then the function itself is m Lipschitz continuous. Okay, this lemma states the converse, but without any assumption on convexity of u. Okay, so if we know that the function is m Lipschitz continuous, which means that for every 2 points xy in the domain, the distance between their images is less than m times the distance between x and y, then actually the derivative which exists, which is assumed to exist, is less a norm than this constant m. Okay, this is very easy actually to prove. It's not difficult, and maybe you encountered it before, because at least in for functions from R to R, because can just take the ratio. Okay, just divide by x minus y, and let y tends to x, and you get the result. So the proof is not. So this is the idea actually, but for general maps between normal spaces, we have to be a little bit more accurate. So we take an arbitrary point x in U, and we pick an arbitrary element h in the source space E. Okay, we know from the appendix of section 2.1 actually, so when we talked about the Gâteau derivative, that when f is Frechet differentiable, then its Frechet differentiable coincide in the direction h coincide with the Gâteau derivative in the direction h. Okay, because here we are assuming something. We are assuming Frechet differentiability. Now it's possible that this limit exists, but this does not exist. But when this exists, it's necessarily equal to this ratio, limit of this ratio. Okay. So in particular, the norm of this fraction tends to the norm of the Frechet derivative in the direction h. Okay, because norms are continuous. Okay. So if now we take t small enough, since x is open, then x plus th belongs to u, and actually this is what we used here, because once again this is where we need the assumption of openness, because we need to ensure that x plus th belongs really to u in order for this ratio to be defined. Okay. Now if we apply the Lipschitz condition, we get f of x plus th minus f of x is less than the constant m times the difference, the norm of the difference between x plus th and x with just th, and I can put t outside, so I get m absolute t times h. So when I divide by t, or absolute t, we get that the ratio, the Gâteau ratio if you like, is bounded for all t small enough by m times h. So when we let t tend to 0, so as you know, limits conserve inequalities, so we get that the limit of this norm is, which is the norm of the derivative in the direction h, is less than m times h. But x was arbitrary and h was arbitrary, so therefore this precisely means that the norm, the operator norm of f prime of x is less than m. Because recall that f prime of x is not necessarily a number. In general, it is a linear bounded map. So by definition, the norm of f prime of x is less than m, and that's it. Okay, so this is very easy. Okay, so now we go back to the proof of theorem 3.6. So now it's very easy actually. So we introduce an auxiliary function for zeta and u. We set g of zeta to be f of zeta perturbed by this linear term. Okay, so f of zeta minus f prime of a times zeta. Okay, so what can you say about G? So first of all, G is differentiable because this is differentiable and this is linear continuous. So the derivative of this term is just f prime of A. So G prime of zeta is just f prime of zeta minus a constant, actually. Second thing, if I write G of x as f of x minus f prime of x and G of y, same thing, and subtract the two, I get f of x minus f of y minus f prime of A times evaluated at the difference because f prime of A is linear. Okay, and now it's very easy because now continuity of G is actually equivalent to the strict differentiability. So suppose first that it's better instead of going by equivalence, it's a little bit better to split the two implications because you understand better. So suppose first that f is strictly differentiable at A, and that epsilon be given. Okay, by definition, strict differentiability means that if x and y are near enough to A, so in some ball of center A and there is delta, then this quantity norm is less than epsilon times the norm of x minus y, which is just the norm of g of x minus g of y. Okay? So therefore, G is epsilon Lipschitz continuous. So instead of M, I have epsilon. Maybe not through whole the domain, but at least in this ball, in this convex set. But anyway, we don't need the convexity here. So the previous lemma tells us that the norm of G prime is bounded by epsilon inside this ball. Okay, this is the lemma. Okay, and but G prime of Z is just f prime of zeta minus f prime of A by 0.1. So this means that f prime of zeta minus f prime of A in norm is less than epsilon for all zeta in the ball of center A and the result, or if you like, if zeta minus A in norm is less than delta. So then this is just continuity of f prime at the point A. Okay. Because usually the delta depends on epsilon and A. Okay. So this is one way. Conversely, if f prime is continuous at A, it's the same reasoning actually. So as we observed, continuity of f prime at A implies that G prime of zeta is bounded by epsilon in some ball around A. And the mean value theorem now tells us that G is Lipschitz continuous on the ball, on this ball. And this precisely means that I just replace G of x minus G of y by its value. So, and this is precisely the strict differentiability of f at A. So now we understand why in the first example, when we took x squared sine 1 over x, why f was not strictly Frechet differentiable at 0. Because if you compute the derivative, we get this. So f prime is 2x sine 1 over x minus cosine 1 over x if x is different from 0 and 0 at 0. And you see here that f prime is not continuous at 0. So this explains why f failed to be strictly Frechet differentiable at 0. Okay. Yeah, and of course we can end by a corollary. So we have an equivalence between, so f of class C1 on the whole domain, if and only if f is strictly Frechet differentiable on the whole domain, which means, as usual, as you expect, strict Frechet differentiability on U just means strict Frechet differentiability at every point of U. Okay, so this clarifies this mysterious definition. So strict Frechet differentiability is just C1. Okay, so that's it. And essentially, this was due to the mean value theorem. So this concludes this section and this video. So thank you for your attention and see you next time.